All right, let's continue to look at functions. We're going to look at patterns and specifically linear functions for this lesson. Our objective today is to identify and represent patterns that describe linear functions, specifically that kind. Before we do that, we need to look at different variables. So when you look at this scene right here, let's identify quantities in the picture that can vary. So we're looking for ones that vary in response to other quantities and look at the relationships. So like for instance, the number of kids on the playground here, does that stay constant or does that vary? And if it does vary, what might it be dependent on? Would it be dependent on what time it is? Would the number of kids in the playground depend on what the temperature is? Maybe considering the shadows. Okay, so the shadows that's being casted, is that dependent on the temperature? Is that dependent on the time? Different things like that. So as you look, there's different variables that are depending on each other. Well, in the solve it, you identified variables and their value depends on the value of another variable. Well, in a relationship between two variables, as they interact with each other, there is a dependent variable and it changes in response to another variable. It's dependent on the other one. The other variable called the independent variable. Values of the independent variable are called inputs. Okay, and the values of the dependent variable are called outputs. So our dependent variable is an output. Our independent variable is an input. And we'll talk more about that as we investigate that relationship. Our central understanding is the value of one variable may be uniquely determined by the value of another variable. One affects the other. Such relationships may be represented as a table, words, equations, set of ordered pairs, and graphs. And we're going to do that on this one with problem 1. In this diagram below, we're going to look at the relationship between the number of rectangles and the perimeter of the figure they form. And we're going to represent that in many different ways. So in this particular situation, we can see rectangle 1, 2, 3, and 4, and how they change as we add rectangles. So we're going to let x be the number of rectangles that happen, because that is our independent variable, and y be our perimeter of the figure. This is our independent variable. Because our perimeter is dependent on the number of rectangles that are involved here. So let's go ahead and look at our table. As I increase the number of rectangles, our perimeter, of course, will increase. And when I look at my different numbers and values, I can see that I have two one-sided figures, and that's represented here. I can see that I have 2 6s, which is represented here. And by adding them together, I get the perimeter of 14, which I can represent as an ordered pair of 114. So when I get to the second one, when I include another rectangle here, I can see that something is changing. I can see that in my second rectangle that now I have 2 ones played out here, and here is another set. So this is changing right here, keeping up with my number of rectangles. It's increasing. Now notice my 12 here doesn't change because the height or the length of this does not change. This is staying constant all the way through here, and that's why we can see that that continues to remain the same. But something is changing as we play along here. When I add a third rectangle, you can notice that it is changing, and thus I need to keep up with it. There is a 1 up here and a 1 down here, and I've tripled that. And same with the 4. When I add 4 rectangles, I'm noticing that I have 1 and 1 here, which is the 2, but I have 4 of them, so I'm quadrupling them to keep up with the changes. And that can be represented as ordered pairs. So I can use this table and play it out as I look for a pattern in the table. So I'm looking for a pattern and describing the pattern in words so I can write an equation. So I'm looking for a pattern. I got to look for a pattern so I can describe the pattern so that I can write my equation. And that's ultimately my goal, is to get to that equation. When I multiply the number of rectangles in each figure by 2, I get the total length of the top and the bottom sides of the combined figures. Okay. Then I need to add. So I need to multiply by 2 and then I need to add 2 and the 6 on my 12 to get that total length that we were talking about is nice and constant on everything. And that'll give me the perimeter if I add those together. So I can build my equation in this fashion. I'm doubling the top. I'm including that constant that's playing on all sides. So I have my equation for that one. And that's going to bring me to my graph. My graph is my independent variable down here is happening with the number of rectangles. And this on the side here is going to be my perimeter. So my perimeter is definitely increasing as I increase more rectangles. And it would, yeah, and this plays out in that fashion. One of the trickier things is trying to find that constant number that keeps showing up. So that's something to keep an eye on. How do you indicate or locate your constant in that situation? I want you to give it a try. So you try it in this diagram below. What is the relationship between the number of triangles and the perimeter? So we've got number of triangles, which is varying, and the perimeter, which is varying. You're going to need to identify your independent and dependent variable, which will show you your x and your y. Go ahead and get me an equation, and go ahead and graph that. Press pause. Let's see how you did. All right, let's check out your answers. In my chart here, I can see that it is changing +4 each time. So this is helping me identify my constant. I can also find, actually, it's not my constant, that's my coefficient in this situation. My constant is actually playing out over here. A lot of times, if you go ahead and come back to the 0, you can find where your constant is by backing up 4. This is where 6 is. So you can see your constant when you consider 0 triangles. And it's true that 0 triangles have no perimeter, but when we look at the pattern, 0 triangles does get us to 6, which does allow us to find our constant. And again, our 4 is our coefficient as we see the pattern play out. We can see that this relationship is linear. It's creating a nice line in this one. It's a constant pattern, keeps playing out. What happens if you do know the perimeter, and I'm just going to increase the triangle? So if I know the perimeter and I'm going to increase one more triangle, I can identify in my pattern here that if I go one more triangle over, I'm just going to add 4 each time. So my answer for that one is I'm just going to add 4 to that situation. If I know the perimeter of a triangle and I go up one more, it's just going to be added 4 to that. If we look at the C, how does your answer to part B relate to the equation you wrote in part A? I'm going to show you the answer here. The 4 times part of the equation means that for each triangle, the perimeter is increased by 4. You know that the perimeter of n triangles, then the perimeter would be 1 more than the triangle is added, which will increase by 4. You can describe a relationship in problem 1 by saying that the perimeter is a function of the number of rectangles. That the perimeter is a function of the number of rectangles. A function is a relationship that pairs each input value with exactly one output value. This is important. It's going to give you only one, and that identifies a function happening. You remember these function machines. You have seen that. One way to represent a function is with a graph. A linear function is a function whose graph is a non-vertical line or part of a non-vertical line. It's actually a nice, when you see the word linear, you see the word line because it creates a nice line for that. This is something we talked about earlier. An input value comes in. Function does exactly one output on that one, which is your dependent variable. Representing a linear function. For example, in photography, the table shows the relationship between the number of photos x you take and the amount of memory y in the megabytes. So we can see that our independent variable is going to be the number of photos I take, because the amount of memory is dependent on the photos I take. So that would make it our dependent variable, thus it goes on the y. So we're looking at the relationship and wondering, is it linear or not? We're going to look at that relationship. So there's my table of information. I copied it back down here. So we know that the amount of memory left given the number of pictures taken as shown in the table. What we need is another representation. And our plan is we're just going to be looking for a pattern. The amount of memory is uniquely determined by the number of photos you take. Okay, so this memory depends on this. You can press pause and play this out if you'd like, and then come back and see how you did. I'm going to keep going though. All right, so this shows us, number one, the memory is 512 megabytes before any photos is taken. So that's nice. If we know where our 0 is, that tells us something about our equation. The second thing is we look for a pattern. It is changing by 1 each time. The third thing we can recognize here is the independent variable x increases 1 each time. And that tells us something, so that's good. We're going to look at the y part over here as it's changing. We're looking for a nice consistent relationship. If it's consistent, it verifies that it's linear. And it is consistent, but this time it is going down by 3, which makes sense. It's using memory. So this does tell us the dependent variable y decreases by 3 each time x increases by 1. X goes up 1, y goes down 3. The amount of memory left on the chip is 512 minus the quantity 3 times the number of the photos taken. So my equation is built out like this, and I can see it play out in the pattern here. I can see that it's a nice consistent pattern. So that's going to give me my coefficient of -3 changing each time depending on what x is. And then I can also see that at 0, I can see my constant, my starting point at 512. And it's going to change, go down each time I take a picture. So however many pictures I take times the 3, and I will subtract that out. My graph will verify that it is linear. Nice straight line moving down. As photos are taken, my memory drops. Let's give you a chance to try it out. The relationship is shown, whatever it might be. Go ahead and describe this relationship. Try words, an equation, and a graph. Press pause. We can see here that it goes up by 2 each time. My output increases by 2 each time, and that will indicate to me how much it's changing each time x is changing. This is important because this is, I got to look at each time. So each time x changes, y doubles, and I need to pay attention to that. I can also see my constant at 0 because that is where it starts. I have to add 8 on as my starting point, and we can see that showing up in the graph. At 0, it's 8, and then increases in a nice constant pattern, which does show that it is linear. I like the reasoning one. Does these ordered pairs here represent a linear function? Now, at first, one might say, yes, it does, but there's one interesting thing. Remember what I said was important a while ago? For each input, there has to be exactly one output. And in this case, you can say, no, it is not, because the input value of 1 actually has 2 inputs, or 2 outputs. Here's 1, and here's another one. And so if that happens in that situation, we could say that this is not a linear relationship. That's it. Make sure you practice that whole thing. I'm going to go lasso a llama.